So now we're going to talk about dynamic branch predictors. That is, branch predictors that change what they predict based on what the branch does as it's running. So how do we record a branch's history? That is, how do we keep track of what the branch has done? If we've got a history here, we've got not taken followed by a whole bunch of takens, we want to keep record of that so that we can predict that the next branch will be taken. So to do that, we need to store some information. We need to store if the branch was last taken or not taken. We need to do this for every branch in the program. And then we need to be able to check this when we load the branch so that we can predict what to do. So to do this, we need to have a table of bits in the processor. So a bit for every branch, where if the bit is 1, it means we think the branch is going to be taken, and if the bit is 0, we think it's not going to be taken. So let's take a look at this. Here's our table of bits. So we've got a 1-bit branch predictor. We can have 5 different branches here. And here's our code, and you can see that each one of these entries points to another branch in the program. We update these entries based on what the branch did last time. So if we go in and we see that a branch is taken, we go and put a 1 in there, and if we see if it's not taken, we put a 0 in there. So this 1-bit branch predictor gives us information on what the last branch was that the instruction took. So how do we update this? Here's our branch table and our code before we figured out what the branch is doing. We're going to go ahead and execute some instructions. So we go ahead and start our code and we get to the branch, and we're going to predict the branch is not taken. The reason for that is that our table here has a 0 for that branch, which means we believe this branch is not going to be taken. Now we go ahead and start executing code, but if we later discover the branch was taken, well, we need to go and squash the instructions that we started running because they're incorrect. We need to update the table with the new information that we expect the branch to be taken. So I'll go ahead and update our table. Now we've got a 1 for that branch. And now we can go fetch the right branch destination and start executing again. So we go through and execute our code, and this time, when we get to the branch, we'll predict it's taken because now our table has a 1 in it for the branch, which indicates we think the branch will be taken. And then we go ahead and we keep executing our code. So, are there some problems with the 1-bit branch predictor? So does what the loop did last time help us predict what it will do this time? Let's take a look at some examples. So here's our loop here. We're going to go around 100 million times and do something. So in this case, a 1-bit branch predictor works great. We're going to mispredict the first time, because we haven't seen the branch before, and we're going to mispredict the last time around the loop. But for 99,999,998 iterations, we're going to get it right. So in this case, the dynamic branch predictor that learns what you did last time is going to work excellently. How about this code here? This is slightly more complicated code. Here we've got 2 loops. We're going around 100 million times for j, and then we've got a loop for k in the middle, which is going around 10 times. How accurate is it here? So what percentage of mispredictions do we do for the k branch with a 1-bit predictor? Well, the answer here is 20%. So we're going to mispredict twice for every iteration of the loop. The first time we go around the k loop, we're going to mispredict because the last time we went around, we exited the k loop, so we're going to predict it's not taken. And then we're going to go around 8 times in the k loop until we get to the last iteration of the k loop. And on the last one, we're going to mispredict that we go around again when we really exit. So that's 2 mispredictions for every 10 branches in the middle loop. So that's 20% misprediction rate. So, if a 1-bit branch predictor isn't good enough, what if we used more bits? So how about a 2-bit branch predictor? Instead of just keeping track of what the last branch was done, what if we have more detailed branch behavior because we store more information about each branch? So here's a 2-bit branch predictor. We're going to have a predicted not taken state, so that's 0, 0. And if we're not taken, we stay there. But if we see a branch that is taken, we're now going to go to another state. We're going to go to the 0, 1 state, but we're going to still predict the branch is not taken. So this other state here is a weak not taken state. It's basically a chance to have one branch predicted incorrectly, but have us still think that it's likely the next branch is going to be not taken. So what this allows us to do is if we saw a taken branch and then a not taken one, we still predict not taken, so we don't have many incorrect predictions. However, if we have another taken branch, now we're going to go and we're going to predict taken. So we're going to switch to predicting taken after we've seen 1, 2 takens in a row. Now when we predict taken, we're going to keep predicting taken as long as the branch is taken. If the branch is not taken, we're going to go into another state where we still predict that it's taken, but this is a weak taken state. This is a chance for us to be wrong about the branch but still predict that it was taken. So we had one branch that was not taken. If the next one is taken, we go back to the strong taken state. And again, if we leave the predicted taken state and we have from the weak state and we're not taken again, then we're going to go and not predict not taken. And this is because we had 2 not takens in a row. So with a 2-bit branch predictor, we now have more detailed branch behavior. We have the ability to keep predicting the branches taken even if we've seen one branch that wasn't taken. So how does this branch predictor work if we're predicting correctly? So if we're predicting not taken and the branch is not taken, we keep predicting not taken. If we're predicting taken and the branch is taken, we keep predicting taken. How about if we have one misprediction? So one branch that does something different. What happens? So we're predicting not taken, and we stay there as long as the branch is not taken, but now we have one instance where the branch is taken. Well, in this case, we go to predict not taken still, but this is the weak state. So we stay there as long as we have another not taken. Similarly, if we're predicting taken, we stay there, and then if we have one not taken, we're going to go to predicted taken. So with one misprediction, we keep predicting what we saw before, hoping that that was just a fluke and we'll go back to what we thought we had before. And that's what's going to happen. So if we're in weak predicted not taken, and we see not taken again, we go back to predicted taken, and it was just one branch that was done wrong, but our prediction was still generally right. And the same thing is true if we're predicting taken in the weak state. We're going to go back to the strong predicted taken state. But what if we were really wrong? What if we have 2 of mispredictions in a row? So we predict not taken, then we see a taken and another taken, and now we go and actually start predicting taken. So we've changed our prediction. Similarly, if we're predicting taken and we see one not taken and another not taken, we go on to predict not taken. So let's take a look at an example here. Say my predictor's in the state where I'm a strong predicting not taken. We stay here as long as the prediction is correct. So as long as the branch is not taken, we keep predicting it's not taken. But if we have a misprediction, so the branch was taken when we predicted it wasn't, now we go to the weak predicted not taken state. If we had a second misprediction, we decide that things have changed, and now we're going to change our predictions for the future, so we move to the taken state. And this is because we've had 2 takens in a row. And then we're going to stay here as long as we continue seeing that the branch is taken. So we've seen 1-bit and 2-bit branch predictors, and obviously you can build arbitrary numbers of bits of branch predictors. The basic idea here is this is saturating counter. So you stay in the state which has the majority of the branches that you've just seen. So you can build these as big as you want. And how well do they work? Well, here are some results for Spec 89, and this is for 4096 entry branch predictor with 2 bits of prediction. So that is, it can handle 4096 separate branches, and we have a 2-bit branch predictor for each one. And you can see here that on some applications, you're getting an accuracy of greater than 90%, so 1% miss ratio. And on a few applications, you're up at about 16% miss ratio. But this is still far better than any of the static predictors we saw before. So here's a question about the 2-bit branch predictor performance. How well would it do on the K loop that we saw before? Well, the answer here is it's going to have a 10% misprediction rate. And the reason for this is because we remember 2 bits of information, we're going to always predict that the K branch is taken. So we're going to be wrong one time every time we go through the K loop, and that's the last one when we exit the K loop. Otherwise, we're always going to predict it's taken because we'll never see 2 not takens in a row for the K loop. And because we never see 2 not takens in a row, we're going to stay in our taken prediction. So it's a lot better than what we saw before. For the 1-bit predictor, we had a 20% misprediction rate. Here we're going to have a 10% misprediction rate. So how well would a 3-bit branch predictor do on this loop? Well, a 3-bit branch predictor is going to be the same as the 2-bit one. We're already, with a 2-bit branch predictor, keeping the prediction that we're always taking the branch. A 3-bit branch predictor just means we keep it even more strongly, but it's not going to detect the pattern correctly. To do a better job predicting this branch, we need to know that every 10 times we go to that branch, we're going to do something different. So that's a much more complicated predictor.